Hello friends, you are watching Prakash the Electromaniac show. Welcome to all. And in our previous lecture we have discussed single line to ground fault, that means LG fault, and its analysis. Right now in this lecture we will try to discuss for the line to line fault for the unsymmetrical fault analysis.
The line to line fault, here the three-phase generator is taken and the neutral of the generator is grounded to the neutral impedance ZL. The generator is considered at initially running at the no load, and we are creating a fault on the B and C phase. So B and C phase are sorted with a fault impedance ZF, whereas the phase A will remain as it is open. Now, looking from this figure, we can write down the terminal condition as IA is equal to 0 because this terminal is open, and IB is equal to minus IC because whatever the current is flowing from the B phase, that the same current is returning from the C phase. The conventional direction of the B phase and C phase current that are coming out to the generator. So here the C phase current is entering into the generator, hence we are considering as a minus IC. So IB is equal to minus IC, and this is the equation number 1. Here this point voltage is VB and this point voltage is VC. As B phase is leading with respect to C phase, so always the current will flow from the B phase to the C phase. So voltage difference between B phase and C phase, VB minus VC, is equal to voltage drop in this fault impedance. So voltage drop in the fault impedance is IF into ZF. But the fault current is the same as the B phase current, so we can write down VB minus VC is equal to IB into ZF. This is the equation number 2. Now, the relationship between the sequence current and the phase current are given by a matrix form. So this is the matrix of the sequence component of the current. This is the matrix of the phase current, and this is the A phase matrix. Now we are putting the value of B phase current and C phase current using equation 1. Equation 1 says that IB is equal to minus IC and IA is equal to 0. So if we place that value, the matrix will become like this way. And if we open out this matrix, we will find out that IA0 is equal to 0, IA1 is equal to 1/3 alpha minus alpha square into IB, and IA2 is equal to 1/3 alpha square minus alpha into IB. So again, if we can rearrange, then we can say it is minus 1/3 alpha minus alpha square IB. This is the set of equation number 3. So again, looking from these two, we can say that IA1 is equal to minus IA2. So this is another important relationship between the sequence current for the line to line fault. For the line to line fault, the current is not passing through the ground. So the zero sequence current is always 0, and the positive sequence current and the negative sequence current are equal in a magnitude, but they are out of phase by 180 degree. This is the equation number 4. Again, we know that relation between the open circuit sequence voltage and the sequence current. This relationship is given by this matrix. So we know the value of IA0, IA1 and IA2. So we are placing that value over here. So zero sequence current is 0, IA1 as it is, and IA2 at writing as a minus IA1. And if we open out this matrix, we will get VA0 is equal to 0, VA1 is equal to EA minus Z1 IA1, and VA2 is equal to Z2 into IA1, minus minus will be cancelled out. So again, for a line-to-line fault, uh, zero sequence voltage is a 0. This is the set of equation number of 4. Now, equation number 2, VB minus VC is equal to IF into ZF is equal to IB into ZF. So we know the relation between the phase voltage and the sequence voltage, phase current and sequence current. So we are writing that VB is equal to VA0 plus alpha square VA1 plus alpha into VA2 minus VC is equal to VA0 plus alpha VA1 plus alpha square VA2 is equal to IB is written as IA0 plus alpha square IA1 plus alpha IA2 into ZF. This is the well-known relationship between the sequence voltage and the phase voltage, or the sequence current and the phase current. So again, if we place the value that earlier get the zero sequence voltage is 0, zero sequence current is 0, and the VA1, VA2 voltage that we are getting from the equation 4. So if we place that value, we are getting the following equation. And again, if we rearrange this term, then we can get alpha square minus alpha into A minus alpha square minus alpha into Z1 IA1 minus alpha square minus alpha into Z2 IA2 is equal to alpha square minus alpha into ZF into IA1. So simplifying this equation, we are getting EA minus Z1 IA1 minus Z2 IA2 is equal to ZF into IA1. So EA is equal to IA1 into the bracket Z1 plus Z2 plus fault impedance plus ZF. So we can get the positive sequence current IA1 is equal to EA divided by Z1 plus Z2 plus ZF. And this is the equation number 5. Again, we know that the B phase current is equal to IA0 plus alpha square IA1 plus alpha IA2. So again, we know the value of IA0. Just we have calculated the value of IA1, and IA2 is equal to minus IA1. So if we place IA0 is equal to 0, IA2 is equal to minus IA1, so alpha square minus alpha. So alpha square minus alpha, and IA1 value is equal to EA divided by Z1 plus Z2 plus ZF, that is derived in a previous slide. And alpha square minus alpha, if you take the factor difference, we will get the value minus J root 3 EA divided by Z1 plus Z2 plus ZF. So we are getting the IP equation in terms of positive, negative sequence impedance, phase voltage, and the fault impedance. IB is the fault current. So this is the equation of the fault current for the line to a line fault. This is the equation number 5. So from equation 4 and equation 5, we can draw this figure. Here the positive sequence network, this is the negative sequence network, and if we connect like this way, we can say that IA1 is equal to minus IA2, because the conventional direction of the IA1 is coming out from the positive sequence network. Conventional direction of IA2 is coming out from the negative sequence network. And if we write down or to calculate for the IA1, so IA1 is nothing but EA divided by 1, 2 and 3 impedance, Z1 plus Z2 plus ZF. So this equation is used for the calculation of the line to line fault, and if you remember this figure, you can calculate line to line fault current for the any fault location, provided that the fault impedance, a positive sequence network and the negative sequence network is unknown to you. For this, a zero sequence network or zero sequence voltage or current are absent because the line-to-line fault doesn't involve any ground or the neutral. Thank you.